Hello students, my name is Shashank Shekhar. So today is the sixth day of our class of the chapter that is electrochemistry. So we'll continue with our previous topic. Okay. So I was saying that we have two parts of electrochemistry, and the first part was mainly about the Nernst equation and the Gibbs free energy. Basically, it was about the EMF calculation and all. And in the next part, we will see that how this EMF calculation is the final thing now. So how this current flows. So that phenomena is the thing that we started yesterday in the previous lecture, you can say. So considering that topic, so if you consider that topic, so we have covered so far these things, right? So we have covered this EMF up till EMF for the first part, and then we have started our conductance and all, and we have seen the molar conductivity. So up to molar conductivity, it's over. So let me give you a quick revision of this second part, introduction, right? So the first thing was conductance. So what was conductance? So it was basically the reciprocal of resistance, and it is the ease by which current can flow through an electrolytic solution. And it was given by 1 by R. So G was equals to 1 by R. G was the symbol of this conductance. Then we have moved to say specific conductance, in which I said that it is that resistance of the body when the substance which is used is present as 1 meter cube, and the length is also 1 meter, such that the cross sectional area is 1 meter square. Okay, then in that condition, whatever will be the resistance will be is equals to its specific resistance, and its formula was given by R is equals to rho L by A. So rho was the specific resistance here, so you can write it as rho as equals to R A by L. Moving forward, then we have seen that if we again take the reciprocal of that specific resistance, then we term that as specific conductance. What specific conductance? So it was basically 1 by rho. So we will write R is equals to rho L by A, then rho is equals to R A by L. Therefore 1 by rho is equals to 1 by R into L by A. So 1 by rho, I have told you right now that it is our specific conductance, and its symbol is kappa. So kappa is basically equals to L by A, and 1 by R is conductance. So kappa is equals to L by A G. So this was our complete formula. Now this was our specific conductance, and one more thing, important thing, specific resistance is also termed as resistivity, whereas specific conductance is often called as specific conductivity. If further we move out to our next topic, that is equivalent conductance, or then we have molar conductance. So speaking of equivalent conductance, it was that conductance which was offered by a volume which contains 1 gram equivalent of that electrolyte. So it is that current which is offered, which is due to the ions that is present in 1 gram equivalent of that substance, that will be termed as equivalent conductance. And the relation between the equivalent conductance and this specific conductance was, say, lambda is equals to kappa into phi, where lambda is our equivalent conductance and kappa is our specific conductance. Okay, and it was multiplied with phi. What was this phi? So this was that value which contains 1 gram equivalent of that electrolyte. So this was our equivalent conductance. Now we have seen a special case. When will these three equal? That is conductance, specific conductance, and equivalent conductance. So we said that if we take an electrolyte and we keep it such that its volume is equals to 1 meter cube, and the electrode are placed 1 meter apart from each other, then in that case we will have a area, that is cross sectional area, of course, is equals to 1 meter square, and the distance as, or the length of the wire, in this case electrolyte, as 1 meter. So in this case, we will say that our resistance is equals to our specific resistance. So this is the very definition also. Now we have assumed, or we have put upon one more barrier, is that 1 meter cube of electrolyte which we are taking is containing 1 gram equivalent of that electrolyte. So this was our third barrier. So in these conditions, so if we apply all this condition, 1 meter cube area, 1 meter apart electrode, and 1 gram equivalent in that 1 meter cube electrolyte, then in that condition, conductance is equals to specific conductance, and that will be equals to equivalent conductance. So this was our spatial relation. So why I am saying all this? Because this term will be used now when we will study some laws regarding these terms. Okay. So the last one was molar conductivity. So what was this molar conductivity mainly about? So it was that conductivity which was offered due to the ions present in 1 mole of that electrolyte. So did you get my point? So basically I am saying that it is that conductivity which is offered by ions that is present in 1 mole of that electrolyte. So up till this part we have covered. So this was the part of the second part of the electrochemistry that we have covered. Today we will see their variation with concentration. So what is the variation of concentration? Variation of course conductivity, with concentration. And we'll study some laws regarding that. So up till Kohlrausch Law, basically today we will cover. So here is our today's topic. We will start with variation and go to Kohlrausch Law. Speaking of which, we have our detailed topic here. So the first one is measurement of conductivity. So we'll see how we can measure this conductivity. So first of all, to observe the change, we should know how to measure it. Then only we'll be able to observe the change it with variation. Then we'll see a tool which is called as conductivity cell. So this is used for the measurement of conductivity. Okay. Then we'll see a cell constant, which is a property of this conductivity cell. At last, we will use this conductivity cell in the Wheatstone bridge so as to we can just calculate our conductivity. So as we have now calculated, or you can say measured our conductivity, we can use this conductivity values for different laws. The first one is Ostwald dilution law. It's very important. So this one. Second is Debye-Huckel-Onsager equation. And the third one is Kohlrausch law. So if I tell you out of this which one is more important, so I would suggest you that this one is the most important. Kohlrausch law. I'm not saying that other are not that much important. To understand this Kohlrausch law, you must have an idea, proper concept of all these concepts, of all these topics to study this Kohlrausch law. But this Kohlrausch law is the most important one out of this all. So let us start with the measurement of conductivity. So we have studied in physics that we use our, say, Wheatstone bridge. So you must have seen that Wheatstone bridge. So we will study this thing later on also. So we use that Wheatstone bridge to, say, do our resistance calculation. Then we can use it to calculate resistivity. Simultaneously, we can calculate our conductivity and conductance. But the problem with our electrolyte solution, or you can say the difference between our electrolyte solution and our metallic wire, is that we cannot pass a DC current across this electrolyte solution. It will result in quick, say, rise in our voltage, and then it will fall abruptly. So there will be no flow of current, continuous flow of current. Secondly, it is very difficult to conduct such a large volume of electrolyte to our Wheatstone bridge, because Wheatstone bridge is mainly of wire and it is somewhat complicated to connect with our say primitive cell. Okay, so this were the two challenges which was faced during measurement of conductivity. So to overcome this, what we have done, first we have used, the first problem was tackled by using alternating current or oscillating current, that is AC. So this current is the current which comes in your house. So we have used this current instead of DC current. So DC current is basically that comes out from our batteries and all. So the batteries you see all around you are the DCs, and this is AC. So this is alternating current. So this is the current you see in our home and home appliances and all. Okay. What was the second problem? It was the portability of our large cell. So what we did that we designed something called conductivity cell. What we have designed? We have designed our conductivity cell. And later on, what we will do that we will use this conductivity cell only in the Wheatstone bridge because it is easy to connect. Then we will use it to calculate our conductivity. So this is our, you can say, algorithm to calculate our conductivity. That we will use a conductivity cell, connect it with our Wheatstone bridge, then acquire our resistance, and with that resistance we will calculate our conductivity. So let us first move to this conductivity cell and try to understand what it is. So here you can see a typical picture of this conductivity cell. So many conductivity cell are available in our market. So two of these I have mentioned here. So what you see here is that you are using a platinum electrode. In both of this, we are using a platinum, or you can say platinized PT electrode. And we have our solution here whose conductivity is to be measured. So we have put this solution here. Okay. Similarly, here I have another conductivity cell. So these are the two commercial conductivity cells that are available in our market. So they both are of different structure, but they are used for the same thing, that is for the purpose of calculating or measuring conductivity. So we will put our solution here and just connect it with our Wheatstone bridge. So it is written about them that there are two platinum electrode coated with platinum black, which is a finely divided metallic platinum as deposited on the electron electrochemically. So what we are doing, we are taking platinum electrode and coating it with platinum black. So it is a type of platinum only, you can say a variant of platinum only. So what we are doing, we are coating it with platinum black. And how we are coating it? Using electrolysis. You must have studied this electrolysis in 9th, 10th only also. So we do a non-spontaneous redox reaction with the help of electricity to coat something, or to coat a metal upon another metal. So we have used that technique only and coated our platinum electron with black platinum. So it is called as platinized platinum electrode. Okay. Now if you see here, they have a cross section area I. Of course this will have a cross section area I, and are separated by a distance L. They are separated by a distance L. So this solution is confined between these electrodes is of column length L and area of cross section A. So what I am trying to say here is that whose conductivity is to be calculated or to be measured is put between these two electrodes whose length is known and area of cross section is also known. Therefore, the resistance can be calculated as R is equals to rho L by A. So its resistance will be given as R is equals to rho L by A. So this is our setup for conductivity cell. Now, what is the utilization of this conductivity cell, or what is the model which make it easy? First of all, see the portability, see the design of both of this conductivity cell. You can just imagine that it is so much portable than our usual cells. Second, we can connect this wire directly to our AC current. Okay, so is this clear? So this is our diagram for conductivity cell. Now, since we have a portable conductivity cell and we know the length and area of cross section both. What do we know? We know the length and area of cross section. So we can calculate the resistance using resistivity, and the formula we know is very clear. R is equals to rho L by A. or we can write it as rho is equals to 1 by kappa. So therefore R is equals to L divided by kappa into A. So this is our equation. We'll know it very well. Now we have seen that we know about the length and area of cross section. So it is a kind of constant. See what it is? It is a constant. So do not get confused with this G star. It is not conductance G. It is a different symbol that is not relatable in any way to our conductance. It is simply a symbol which is G star and it stands for L by A. So what is this cell constant? So it is basically length per unit area, or we can write it in many ways, this equation. So if you modify it further, so we have seen that R was equals to, previous slide, you must have seen that R was equals to L by A into 1 by kappa. So we have replaced 1 by kappa and put it here. So you will get this equation finally. Therefore, your cell constant will be a multiple of resistance and specific conductivity. And this is symbolized by the symbol that is J star. It is symbolized by a symbol that is J star. Sorry, G star. And it is not in any way connected to our conductance. It is just a symbol that is much more different from that conductance. Now, one thing to notice here is that if you have seen in the previous slide, you must have seen a fixed structure of this electrolyte. Means the length, or you can say the distance between the electrons were fixed, and the volume of the conductivity cell was also fixed. So we can kind of say that for a conductivity cell, we have a fixed volume of, or fixed value of the ratio of L by A, and it is written as G star. Further, we can write resistance in terms of G star, that will be equals to R rho G star, because we know the formula very well, which is R is equals to rho L by A. So we replace this L by A to G star and we got this formula. Any problem? Okay. So we have done this. Now, if you want, you can derive various formulas based on this formula. Suppose if you want to say find out rho, or say you have to find out G, it will be 1 by R into, so R is equals to rho L by A. Therefore, 1 by rho is equals to kappa is equals to G, okay, GL by A, which will equals to G star. Okay, we can write this also. So what we have done, so I have brought this rho here and R here. 1 by R is equals to G and 1 by rho is equals to kappa. So kappa is equals to G. L by A is G star, which is the cell constant. So kappa is equals to G star. So you can use this form of say kappa also, in which we have included G star as our cell constant, and it is equals to L by A. This G star is equals to L by A. So you should remember it. Do not get confused that how it will write it. It will be A by A or L by A. Just be confident that it will be always L by A. G star is equals to L by A. Keep it in your mind. So for that, remember a formula that would be easy for you. R is equals to rho L by A. So remember it like this. R is equals to rho G star. And you remember the original formula also. R is equals to rho L by A. You can compare both of this and get your G star as L by A. So we have covered cell constant now. Now we have a conductivity cell whose cell constant is known, and the thing that is to be you can say calculated or measured is now conductivity. So we'll move to now Wheatstone bridge. Okay, we will move to this Wheatstone bridge. So this setup here is basically like this is that we have 4 resistance, 1, 2, 3 and 4. Out of these 4, 2 are fixed, R3 and 4. R1 is variable, we can vary it accordingly, and in R2 we will place our conductivity cell. We will connect our conductivity cell here. Okay, that is, we are here now calculating cell constant. We are known, so we are calculating resistance here. So as I have told you earlier that we know the value of two resistance R3 and R4. So this one and this one. So they both are constant, and we have variable resistance R1. We will see why it is variable. And suppose the conductivity cell has a resistance of R2. One more thing, this is now no more connected with a DC current. It is connected with an AC current or an accelerating current, that is 550 to 5000 cycles per second. Now P is the suitable director. It can be anything. You can connect this with any your application. Like if you can connect it with our headphones, so that whenever the current flows through it, you will get your signal. Or you can connect it with an electronic device or a gate, like something like that. That upon connection, or you can say flow of electricity, a bulb can glow on, or like this. Now the bridge balanced will have no current pass through detector. So if the resistance on both sides is equal in this way, that R2 by R1 is equals to R4 by R3. So if this is the case, so if this is satisfied, R2 by R1, that is this by this is equals to R4 by R3, then in that case we will not see any detector current. Okay, detector showing correct. So since we know the value of these three, that is R1, R3 and R4, we can just bring this formula forward. That is R2 is equals to R1, R4 by R3. Now the thing here to notice that we are using first of all the variable resistance. So first we will connect all these three and we will vary this resistance accordingly until and unless we get a zero deflection in our detector. Okay, so this is our thing that we are doing. So what we are doing, we are taking 4 open areas, out of which in 2 we are putting constant resistance, and 1 we are putting variable resistance, and 1 we are putting our electrolyte whose conductivity is to be calculated. Now what we are doing, we are just making the R3 and R4 constant and varying R1 accordingly, such that the detector shows no current. So as the time comes and the detector shows no current, what we will do, then we will calculate the R2, and we know R1 and R3 already, and since we are varying this resistance, that is R1, so we know the value of R1 also. So we will use this combination here, put all these values R1, R4, R3. What we are doing, we are using this thing, we are using this thing to calculate our R2. So when we are done with this R2, so we get our resistance. We know that R is equals to rho G star, and G star is constant for a given electrolyte. Therefore G star will come here, R by G star, it will be equals to rho. So this is our thing for the Wheatstone bridge. Now we will move to Ostwald dilution law. So first of all, let me make you understand what is weak electrolyte and strong electrolyte. So I have mentioned this earlier also. So strong electrolyte is something which dissociate completely, 100% dissociation occur, and weak electrolyte is something which has not the complete dissociation but a partial dissociation. So for that, we are given with a law that is called Ostwald dilution law. So it is only applicable to our, say, weak electrolytes. Okay. So if you write for a weak electrolyte, then a very good formula for that is that alpha is equals to lambda m by lambda naught m. Okay. What is alpha? Alpha is equals to lambda m by lambda naught m. Now I have already mentioned this term in the previous class. Is lambda naught m. It is molar conductivity at infinite dilution, or the case where the conductivity is maximum. Okay, molar conductivity is maximum. And we have this lambda m, which is the molar conductance of whose conductance we are eager to find out. So basically what we are taking here is that we know the formula. First of all, alpha is equals to lambda m by lambda naught m, where lambda m is the molar conductivity and lambda naught m is the molar conductivity at infinite dilution. Now we take this electrolyte and what we do, AB, and we just keep it in water, so it will slowly start to dissociate. Suppose the electrolyte we have taken is AB, right? And we are saying that C moles of which are dissolved per decimeter cube, means the concentration is given as C, because C moles are dissolved in per decimeter cube and decimeter cube is liter, so C is dissolved in 1 liter. That is our that is our concentration or molarity of that aqueous solution. Now take a thing that alpha will be our degree of dissociation and the fraction of total concentration of the electrolyte which exists in dissociated state, right? Because alpha is that only, it is the number of particles dissociated by total number of particles. So basically here you are given a fraction whose fraction, the fraction of the total concentration of electrolyte which exists in dissociated state. So if you consider the equation, that is AB is going to A plus and B minus, then it would be having initial concentration of A plus and B minus as 0, because we have not done any dilution. So as the time passes, we have our dilution and we have this AB going to A plus. So suppose alpha is a degree of dissociation, okay, it will give you C minus C alpha, where alpha is a fraction of electrolyte that dissociated, or C minus C alpha gives us C alpha of this A plus and C alpha of this B minus. Okay, we got this. Now if you want to write Ka, that would be giving us C alpha square. We know it very well, what is C alpha square. Then what we are doing, we are substituting the value of alpha. We know the value of alpha, it is lambda m by lambda naught m. We are substituting the value of alpha in each of this alpha in this equation. So we'll get this equation finally, right? We'll get this equation finally. If you want, you can evaluate by it yourself. You will get the same thing. So you can see here we have lambda square m by lambda naught square m. So we're basically putting this lambda m by square by lambda naught square m out of alpha. Similarly, we have this alpha here. We put this thing again. So we'll get it as lambda m by lambda naught m. Now we'll multiply this lambda and naught m on both sides, and this lambda naught m will get cancelled and the square will be cancelled out. We are again left with this C lambda square by C lambda naught m, lambda m minus lambda m. Okay, so this equation is very important to calculate C here. And if you consider the graph here, we have this graph which is the change of lambda m, that is the molar conductance with respect to root concentration. So it is basically for acetic acid. So as we increase the concentration, what will happen? The conductivity will decrease. Okay, the conductivity will decrease. So we have here lambda m, we have here root c. So we got this type of a non-proportional graph, in which what we are doing, we are just increasing the concentration and decreasing our lambda m. Okay, is this okay? Yes. So this was most of all mainly for our this was mainly for our weak electrolyte. Why? Because weak electrolyte have only alpha, that is degree of dissociation. Strong electrolytes do not have any such boundaries. It is completely dissociated. So this is only for weak electrolyte. Next, and again important equation. So this is only for strong electrolyte. So what does this equation defines? It is saying that lambda is equals to lambda naught m AC half. So if you compare this thing here with y is equals to mx plus c, you will get that we are having m is equals to minus a, that is slope, x is equals to lambda naught m, that is our intercept, and c is equals to c half. Okay, so this is basically root under concentration. So what type of slope we will get? We will get a slope with a negative value. So this same thing is depicted here. We're getting a decreasing fashion. And then we can see that with increasing root C, we have decreasing lambda m. So upon dilution, we can say that we have our reduce in this conductivity. Okay, is this clear? Right. So this is our intercept mx plus c, that is lambda naught m. Now we can say one more thing about this lambda naught m is that this lambda naught m is maximum when the concentration is 0. What is it? That the lambda naught m is maximum, or you can say lambda m is maximum when the concentration was 0, and lambda naught m is the concentration at infinite dilution. So it is considered as limiting molar conductivity. Okay, is it clear? So lambda naught m, what is lambda naught m? It is the concentration at infinite dilution. Means we are taking a large amount of this solvent and we are putting a small amount of electrolyte, a negligible amount of electrolyte, and whatever will be our say this conductivity or molar conductivity, or will be our limiting molar conductivity. So in this case we can see why it is told limiting, because after this we will get a reduction slope. So as we increase the value of root C, we will see a decrease in this slope. So the slope is decreasing in this fashion. Okay, is this clear? Now we are done with our conductivity and its variation with concentration. So we have seen for strong electrolyte we have a different type of equation. We have for weak electrolyte we have different equation. So this one was for strong electrolytes only. You should keep this in mind. So this is only for strong electrolyte. That is why we are getting this kind of graph. Whereas the previous one, which was Ostwald dilution law, where we saw that we have kind of this. So this was for weak electrolytes. We should compare both of this in a go, or in a time. Weak, it is strong, it is already written weak electrolyte. Okay. So if you see both of this, so one is a decreasing function and the other one is also a decreasing function. Only the difference is that this weak electrolyte upon small dilution also show, or you can say, a rapid decrease in our molar conductivity. So what do I mean by saying that? I mean that both strong electrolytes and weak electrolytes show a decrease in their conductivity or molar conductivity upon increasing the concentration, but this fall is more prominent in our case of weak electrolyte because they fall abruptly. Just as this root C value increases or the concentration increases, we can see a very quick drop in this, say, our molar conductivity of weak electrolyte. So this should be kept in mind. This graph is very important. So one, we have a strong electrolyte graph, one we have a weak electrolyte graph, and we have chosen this thing as our representation. Okay, is this clear? So this is our thing. Now, since we have seen both these equations of Debye-Äckelon-Sager equation and say Ostwald dilution law, now I will move to one more important thing, that is Kohlrausch law. This is the most important part of our today's lecture. So what does this law say? So this law is very simple. If you think it in your mind, it is very simple and quite easy to imagine. So it is a very simple and straightforward statement which says that the molar conductivity of that electrolyte at infinite dilution. What is this? Is the infinite dilution. We are talking Kohlrausch law is only applicable at infinite dilution. This should be kept in mind. So again, this Kohlrausch law is the molar conductivity of an electrolyte at infinite dilution is the sum of individual contribution of its positive and negative ions. So you know that an electrolyte is when it is dissolved in water and its aqueous form, it dissociates into two parts, positive and negative ion. So we are saying that this overall molar conductivity is just the sum of the contribution that is coming from positive and negative ion. So we are adding both of the conductivity of this positive and negative along with their stoichiometric coefficient, then we will get our molar conductivity. So we can write that we know an electrolyte of dissociation, suppose it is giving nu plus, means this much number of cations and this much number of anions. So this is the stoichiometric coefficient I say here. And this lambda naught m and lambda naught minus m are the limiting molar conductivity of a cation and anion respectively. So this lambda naught plus is for cation and lambda naught minus is for anion. So what we will do, we will take the limiting molar conductivity of cation and anion and multiply it by the stoichiometric coefficient, and we will add this and we will get our lambda naught m. Very simple. Suppose we have illustration here like this, that lambda naught NaCl, let me do it with more clearly. Suppose I am just doing some exercise for you. Lambda naught NaCl, it can be written as lambda naught Na plus plus lambda naught Cl minus. Again another example, H2SO4. Now you can see that H has a coefficient of 2, that in that case we will write as lambda naught H plus multiplied by 2 plus lambda naught SO4 2 minus. Another example, HCl, which can be written as lambda naught H plus plus lambda naught Cl minus. No problem. You can write it for weak electrolyte also. So if you have suppose CH3COOH, then we will write as lambda naught CH3COO minus plus lambda naught H plus. Completed. So these are our few examples of this Kohlrausch law. Now suppose you are asked that find the molar conductance or molar conductivity of this. So this all are suppose molar conductivity. Now you are asked that go and find it for CH3COO minus and H plus. It is given here. Okay. Now you are told that find it for NaCl with help of this and this. So how you will do it? Firstly, you will see what are the things that you need. For NaCl, what do we know? We need this Na plus and Cl minus. But here we have only Cl minus. We do not have Na plus. Now suppose one more thing is given, that lambda naught for Na plus is this one. And this value suppose given x. Okay. And we have this, say we do not need this H plus. Both of this H plus we don't need. And we do not need this CH3CO minus also. So suppose we are given in a whole CH3COO Na. Its value is also given. Suppose this is X, this is Y, and this is equals to Z. So what do we don't need? We do not need this H plus, but we do need this Cl minus and this Na plus. So we will add this and this and subtract this one. Very easy. Add this and this and subtract this one. So if you do so, you will get your value for lambda naught NaCl. So slowly I will show you some questions also regarding this Kohlrausch law. Then we'll see some questions. They will get a more clear idea of what is happening here. So basically we have seen the variations. Then we have seen the variations in accordance with laws, that is Ostwald division law, and the what was that law? It was Debye-Huckel-Onsager equation. So we have seen these two. Now we have moved to this Kohlrausch law, and I am telling that this is the most important one. Now the student make mistake here. They forgot to multiply it there with their stoichiometric coefficient. So do multiply it with this. So I have given an example right now. Suppose you have H2SO4. So you will write it as lambda of H plus multiplied by this. It is also not. And SO4 2 minus. And this point is also important, that this electrolyte is present at infinite dilution. infinite dilution. So what is the infinite dilution? So it is infinite dilution. At infinite dilution, we have the maximum value of our molar conductivity. Sometimes a question is linked from this formula. Yeah, it can be linked. Suppose you are given alpha, you are given lambda m. So student make mistake that they directly use this lambda m here in this formula and try to calculate using Kohlrausch law. So you will not do that. You have to put this lambda naught m like this. We'll put the value of both of this to get your lambda naught m, and then you will use that value to calculate our, say, overall molar conductivity. So this was for today's class. So these things I have covered for today's class. So basically we are done with the second part also. Now we have a third part which is independent, not kind of independent, but you can say a combination of both of these parts. It is that application part. So in that part we will see how we can apply this electrochemistry to various parts of life, and it is being applied in batteries and all. So all of this work on the principles that are used in the electrochemistry, like our cells we use in our phones, cell phones, and plus we have this cars which is running on lead batteries and all. Not lead batteries, sorry, lithium ion battery basically. So it is a very quite, you can say, famous field of chemistry, that is electrochemistry, which is attracting more and more scientists to do research in and have a great future. Okay, so this was all about the second part of electrochemistry. Tomorrow we will see the types of cells we have, not on the basis we have concluded earlier. So electrolysis cell, we are left with this electrolysis cell. We will see the Faraday's constant and what is this Faraday's law and all. So I have told you what is Faraday's constant earlier also. So I will give you a brief detail about that. After that, we will see the types of cell based on their use. So where we are basically having two types of cell, primary and secondary. So we will see those also. Okay. So thank you for today's class. With this, I end my lecture.